trying to have diversity in our talks, but I also want to make sure that we hit topics that are of the greatest interest to you. So please just let me know things that you're interested in, and I will work on it for the future.
Okay, thanks, Bruce. Anything from Madam Secretary?
No.
Okay.
But
And
thank you
John,
for asking.
and John Hepler, anything from, oh wait, from either website or observations?
Just a reminder, links to neighboring astronomical societies are on our website. They've been there for years.
Okay. All right. I think that pretty much covers the club business. Don, are we going to do a what's up in the sky, or
Yeah.
do we have John
Will,
Conrad
I
back
said,
in?
I called John Conrad, didn't get an answer, and I'm looking on Zoom here for Eric Jensen. He was here.
Don, he said he was going to step out just for a bit, and he'll be back at 7:45.
Okay, all right, that's fine. All right, well, why don't I give us a quick walk around the night sky then until he comes back. So I'm going to use Stellarium. Now, sometimes this slows down, so please let me know. Speak up if you see it lagging. So this is Stellarium. I think most of you have seen this before. When we have meetings in person, I like to use our Mac computer, which has Sky Safari, but Sky Safari only works on Macs. And for these meetings here, I like to use my PC. So we are on Stellarium. I'm going to go to the lower left corner and activate the menus to stay visible. You notice I set it for Philadelphia, and this is current time. So this is what the stars look like outside right now. But to make it a little easier to see, I like to bring in the constellation drawings, stick figures, and the labels. Occasionally, I like to bring in the artwork, but it gets a little bit busy when you do that. So
Yeah.
work off. Yeah. So there's lots to see in the sky, but I'm going to really take my time and take a look at some of the most spectacular things out there. Now, one change I have to make to the program, I go deep into the controls. I'm going to activate the deep sky objects. All right, and that will bring up all the interesting things in the sky to see. I'm going to start out with Colander 70. That is right here. This whole group of stars is Colander 70. Now, my favorite part in binoculars, this is the great binocular object. If you take binoculars out, easy to find. You know, Orion is probably the most recognizable constellation in the entire sky. With binoculars, there is a beautiful S curve of stars here. Can everyone follow my pointer? Is that working?
Yes, it is. Yes.
Okay, this S curve, it doesn't show out really well here on Stellarium, but it is very distinctive when you see it in person, and it is just beautiful. So be sure to grab binocs, even though it's cold. Go out and take a look, and look for Colander 70, which is here. Nearby is, again, Stellarium has some great names. I can flip a switch.
That Casper one.
I can flip a switch and have it give me the regular names, but I like to have their fanciful names, so I leave it with the fanciful names. So Casper the Friendly Ghost, I wrote about this in the newsletter. This is M78. Now with Stellarium, a little trick is you can double click, and that centers an object. Again, Stellarium is completely free. It'll run on any PC, and you can go down, just search for Stellarium, and you can download it for free, and it runs on a PC. It's so much fun to zip around the universe, really. So here's M78, Reflection Nebula, fairly bright, really bright, you know, magnitude 8 for a nebula. But with, you know, with a 4 or 5 inch scope, you'll easily be able to see this, probably with a 60 millimeter.
Yes, it is.
Pete would know, yeah. Another object I like to point out that doesn't show up so well on Stellarium, but if you go up to Orion's raised arm, we have what's called the 37 cluster. Now, why would you call it that? NGC 2169. Again, I'm going to double click to center, go into his elbow. Doesn't show up so well here, but in a telescope, this really does look like a 37. I've seen many times. It is worth getting your telescope out and taking a look. It actually looks like a 37. And so it's a fun little object to see. And there's some great names for stuff that I've never heard before here. The shoe buckle cluster, I don't know what that is. Poor man's double cluster. So this is the third double cluster that I know of. We have our standard double cluster below Cassiopeia. There is the summer double cluster in Ophiuchus. This one is a new one to me, the poor man's double cluster. Anyone ever heard of that?
No.
I'm going to have to go looking for it sometime soon. NGC 1807. So a little further up, and these are also good binocular objects. Three nice open clusters. M37, which is called the January salt and pepper cluster. The Pingerel cluster, M36. And then right here, M38, the starfish cluster. I'm going to zero in on that one. Again, these are all three nice open clusters. It's nice to compare the three of them because they're all a little bit different looking. So they're fun to view. And if you go a little further down below Orion, near the brightest star in the sky, Sirius, it's not really that bright, but it's close. So that makes it bright for us, the brightest star in our sky next to the sun. The little beehive, M41, another
Hey,
nice,
split yourself. It's hey, Carl. If you run the dishwasher before I'm back downstairs.
another nice binocular object. But of course, it does actually pale in comparison to the real beehive, M44 in Cancer. Now, this is definitely a binocular object. You probably can't get much of this in a telescope. It's so huge. It's a great object to show people in big binoculars at a spring star party, which maybe we'll have. We'll see. See how fast the vaccine comes out.
When you're talking about binoculars, what power are you thinking?
For general astronomy, I think 10 by 50s are a very nice match. You can get by with 7 power by 40, but a 10 will give you a little bit more depth to see into some smaller objects. And the 50, anything beyond 50, it gets hard to hold up by hand. I mean, I like to use binoculars up to 100, but you have to tripod mount them. And even with a 10 by 50, tripod mounting it makes it easier to use. But I would say 10 by 50 is a nice mixed level of binocular to use.
Thank you.
A couple other open clusters down here. They'll be up later tonight. M47, a nice open cluster. M46 right by it, another open cluster. I like open clusters, especially this time of the year. You can go out with your binoculars, see them, and not get too terribly cold. Especially if you get them focused good one time, they'll stay in focus. Well, the ultimate binocular object, of course, is the Pleiades. This is probably the most beautiful cluster in the entire sky.
Wow.
So that's where I'll end. Any other questions on what's up there right now? Well, I think one more moment. The only planet we have right now in the sky, if I can find it, over here toward the west. I'm not making dizzy, am I? I guess I'll have to search for it. Larry does have an excellent search. Okay, there they are. Thank you, Gordon. So the only really bright
Mars
is Mars.
Right.
And I don't know if you heard the news lately about Mars, but Mars is in the news. Some recent data from the Mars orbital imager is saying that this valley, Valles Marineris, it's saying is the largest canyon in the solar system. It is 4 or 5 times deeper and 10 times longer than the Grand Canyon. So
Road trip?
That was in the news lately. Whereas Uranus is not far away. Mars is great to help you find Uranus. And we don't see them from Earth, but Mars has rings. Uranus rings, I'm sorry, Uranus has rings, yeah. Okay, I think I'll end it there. And turn it back over to you, Bruce.
Has Eric joined us back?
Okay, Dr. Jensen's back. Good.
I'm here.
You're here. Good. Okay. So, Don, before we start, John Conrad is definitely not talking.
I don't see him on Zoom. I called him. He hasn't called back. So.
Okay. So just for everyone in the club, what we decided we're going to do now every monthly meeting is after Don gives the tour of the night sky, John Conrad has offered to kind of give us a 5 to 10 minute highlight of updates of new NASA missions, either those that are ongoing or planned, kind of the, brief little sound bites, if you will, from the latest NASA missions. And we were planning to start this in January, so apologies that it's not going to happen tonight. So tonight, though, we're going to have the third and final in a series of presentations dealing with exoplanets or exoplanet discoveries. If you remember, we started in September with Sarah Seeger from MIT. Then in November, we had Giovanna Tinetti from University College London. And tonight we have Dr. Eric Jensen, who is a local guy from Swarthmore. He's a professor of astronomy at Swarthmore. He's been there since 1998 and been trying to get him to come and talk to our group for quite a while. So I'm really pleased that he is. He has a number of interests that I think, we all kind of share. He's very interested in understanding planetary formation around binary star systems and the potential habitability of those planets. In this role, he's currently working with the NASA test mission as the deputy lead of several follow-up groups, and I'm sure he's going to talk about that tonight. He also is working on the KELT survey for extrasolar planets, where he's using transit-based approaches for exoplanet detection. And he actually, I believe, wrote a new software known as Taper to actually help astronomers with this undertaking. And probably not as a surprise, given his interest in exoplanets and planetary formation, he also has a keen interest with some of his biology colleagues at Swarthmore in astrobiology. So tonight, he is going to give us an update on, excuse me, on kind of new discoveries and observations from the NASA test mission to identify and characterize exoplanets. So, Dr. Jensen, it's a privilege. Thank you for joining us.
Thanks a lot. It's nice to be here and glad that I can get the chance to talk to everybody. So let me go ahead and switch over to my screen here. So I didn't realize that you have had quite so many exoplanet talks recently. So hopefully I'll still be able to maybe give you some insights that you haven't heard already, or at least refresh you about some things that maybe you've heard about before. And as far as NASA missions, you mentioned getting some updates. I'm going to try to sort of connect the dots a little bit about some current and some upcoming NASA missions. So I'm mostly going to be focusing on tests, but I'm going to be talking about how that fits in with some other things. Okay, so we currently astronomers know of, and humans know of more than 4,000 planets, 4,300 and some at last count. The number up at the top here is up to date. The numbers in each of these categories are, you can see those don't add up to 4,000. That's a slightly older graphic below. But the bottom line is thousands of planets that we know of outside the solar system. And so you could ask the question do we really need to keep looking for more planets? Is this enough, or what's the, what are we trying to do here? When you think about, I sometimes think about an analogy with you discover a new species or something, and the first one you discover is amazing. And the first few dozen, really, you're learning a lot. And then after a while, you kind of have a sense of what's out there. And so the question is, given the huge amount that we've learned in the last now about 25 years that we've been able to discover planets outside the solar system, what's the next step, or what's the current goal here for trying to continue to look for planets? I mean, knowledge for its own sake is something I'm a big fan of and in favor of, but what's our incremental next hot Jupiter that we discover? What's that telling us? So what are we after, and in particular, why a new exoplanet mission? So this is a mosaic here, mostly of discoveries from the Kepler mission. And so to help us think about this, what I want to do is show you a little animation here first of where, of those 4,000 planets that we know of, where in the sky are they? So we're going to start at Earth, and we're going to zoom our way out to bigger and bigger distances. So here we are right in the middle. There's different ascensions here, and you'll see concentric circles as we zoom in of different distances away from Earth. And you'll see planets pop up that are either in gray, those are planets that were discovered not by the Kepler mission, and in blue that were discovered by NASA's Kepler mission. Okay, so let's zoom out here. So that's 3 parsecs, or about 10 light years. So we first see one there, so 10 parsecs, we're seeing a handful of planets. Now we start to see some blue dots here and there. So up to 100 parsecs, or 300 light years. 300 parsecs, about 1,000 light years. And then our final circle there is 1,000 parsecs, about 3,000 light years. So we can see a bunch of black dots or gray dots in here within a few hundred parsecs, but by far the vast majority of the planets that we know about came from the Kepler mission. And the reason we see this big spike off to the left here is that the way the Kepler mission worked is it pointed at one spot in the sky, and it stared at that spot for about 5 years. And so by far the lion's share of those 4,000 planets we know about are in this one direction. And you can't even see it here anymore, but this inner circle that you can maybe just barely see, that's 1,000 light years from Earth. So most of the planets that we know about are thousands of light years away from Earth. And part of what that means is they orbit stars that are pretty faint. And so it's going to be challenging for us to learn much more about a lot of those planets than we already know. They're tough targets to follow up because they're mostly around pretty faint and pretty distant stars. Okay, so that kind of sets us up to think about, well, what else could we do? So here is a nice graphic that shows the Kepler field on the sky. So NASA's Kepler mission was launched, I think maybe 2014, and was functional for about 5 years, and looked for the most of its mission at just this one patch of sky. That gives you a nice long time baseline on that patch of sky, but there's a lot of sky out there besides that. So so we think about what else we could do, and in particular, what if we do a survey that goes across the whole sky? There's a couple things that we can think about that would be advantages or different kinds of strengths. So the Kepler mission certainly had some strengths. It did some great science. There were some things it could do, there were some things it couldn't do. So one thing that we can do if we go all sky is we can observe more bright stars. So, you look at this field here, there's a real bright star there. You can see, there's a handful of other stars there, but in any given part of the sky, there just aren't that many stars that are all that bright. And, we all like bright stars because they're easy, right? They're, you can take your telescope and you can get a lot of information about those relatively bright objects. So for follow-up and trying to understand planets better, then having relatively bright stars is helpful. And the other thing that we can do if we look across the whole sky is we can get many more nearby stars. So to some extent, these two things go together. Some of the stars that we see as bright are bright because they're relatively nearby, but the vast majority of the nearest stars are actually pretty faint. And that's because stars like the sun are a little more massive than most of the stars out there. So if you know your spectral types, OB, AF, GKM, the sun is a G-type star. K-type and especially M-type stars, which are cooler than the sun, are much, much more common. So there's a ton of nearby stars that are pretty faint. And so in any given field that you look at, you're not going to have very many nearby stars. And so if you want to get a good census of the nearby part of the universe, you need to go to the rest of the sky as well. So some of those nearby stars are going to be bright and some of them are not. But we got to look at more of the sky to try to see them. And the nearby stars are useful also for follow-up, especially if we want to try to think about imaging where you would be able to see the star and to see the planet separately from the star. That's a technology that is continuing to develop and is going to be a big part of looking at exoplanets in the next couple decades. It's something that we can't do with most planets right now, but it's going to be the nearby stars with planets that are going to be the best targets for that. So both of those categories are going to allow us, if we can find those planets around really bright stars, or if we can find those planets around relatively nearby stars, both of those are going to be good for learning more about the planets that orbit them. And the third thing, which I didn't put in my list here, is that if you have objects that are intrinsically rare, weird kinds of planets, Kepler found a few of those, but you need to cast a broader net to try to find those intrinsically rare objects. So here's a space mission that is mostly not what I'm going to talk about, but is really intrinsically linked with the TESS mission. So some of you may be, you all, I'm sure, are familiar with the Hubble Space Telescope, which has been a real workhorse of astronomy for the last 30 years. The successor to Hubble is the James Webb Space Telescope, and that is scheduled for launch this fall. Now it's been scheduled for launch, there's been launch dates that have slipped back for JWST for a while, but it's really looking, more likely that this is going to be the year that this telescope gets launched. And it is quite a machine. And in particular, it is going to be a great telescope for following up some of these discoveries. It's really built to observe cool things, observe faint things, and it's going to do a great job of it if we can find the right targets to point it at. Here's a different picture of that. So this one was an artist's conception, but here is an actual image of the mirrors for JWST to give you a little bit of a sense of scale. So here's a person in the clean room at NASA looking up at the mirror. So this is an 8-meter diameter mirror. So this is a huge telescope, and it's especially a huge telescope to put into space. So the Hubble Space Telescope has a mirror that's only about the size of one of these hexagons. And, so it's done great work, but it's a relatively small telescope by modern standards, 2.4 meters in diameter. And the reason it had that size is that that's the size you can fit in a rocket. The way JWST is going to work is that this whole mirror assembly actually folds up to be put into a rocket. You can see this gap off to the left between those 3 left-hand segments. Those can fold over, the right-hand ones can fold over. So once this is launched into space, the whole thing's going to unfold like a big umbrella. And then they have to align all those mirror segments within a fraction of a micron to be able to make the observations. But hopefully that will all work. So JWST is not my main topic, but it's intimately linked with what the TESS mission is trying to do, which is find great targets around bright stars, around nearby stars that are going to be great targets for us to learn more about other solar systems. So we're kind of setting the stage for that. Okay, now here's the main thing I really am going to talk about. Very different kind of mission than JWST. So JWST is a huge thing, billions and billions of dollars. I don't even know what the latest price tag on it is, but it's big. TESS is a much more modest mission and more focused mission. It's what's called an explorer mission. I'll show you a picture that gives you some scale in a minute. It was a mission that was launched about 2 years ago in April. So successfully up there in space, and it's working well. And it is going to survey over its lifetime most of the sky, about 90% of the sky. And it is taking images of the sky every 2 minutes for a given part. And I'll tell you a little bit more about its observing cadence in a minute. And its goal is to detect of order 500 Earth-like planets, mostly around nearby and relatively bright stars. And it has started that mission already. I'll just point out these 4 things in the middle here. It has 4 different cameras, and I'll show you the arrangement of those in a minute, but it's a sort of an interesting design that it has essentially multiple telescopes that each has its own camera that are pointing in a particular pattern in different parts of the sky. Okay, so since you've had a few exoplanet talks, you probably are familiar with this, but just to make sure we're all on the same page, the planet detection technique that we're talking about here is what's called the transit method. And so here's an example of a transit in our own solar system. They don't happen very often. I hope some of you saw the transit of Venus in 2012 and the one before that, because it's going to be another 100 years till we get another one. Get Mercury transits occasionally, but this little dot right here is Venus going in front of the sun. And so that happens in other solar systems too, where there's some of those planetary systems out there that happen to be lined up just right, so the planet passes in front of the star as we see it from Earth. So here's just a little...
Excuse me, just to let you know that we scrambled all over southern Chester County to make sure that we saw the transit of Venus.
Nice.
Liz
Cool.
probably remembers that.
I was getting the 2004 transit, 2004, is that right? The first one, I was giving a talk at Gettysburg, and it happened to be cloudy there, so I missed it. But then I saw the second one, so I did get to see it.
That's cool.
So the idea here is illustrated in this little animation. So in the top, you got a planet going across the star, and we can't see that, but what we can do is measure the brightness of the star. And if we can measure the brightness of the star very precisely, then we see that it gets a little bit fainter during the time that the planet is in front of the star. And as the planet keeps going around, then that pattern repeats. And the amount that it gets fainter depends, of course, on how big that planet is compared to how big the star is. Here's the same kind of idea, but just showing a different animation of it. And the thing I just wanted to emphasize here is that, again, it keeps repeating. And so the idea is if you see one dip, that doesn't tell you that much, because we all know we can get, a little bit of clouds or poor transparency, and it's hard to judge just from that. But if you see this repeating pattern, that's something that tells you there's something repeatedly blocking the star. So that's the idea. So here's some real data, and we're going to see some other plots like this. So let's make sure we all are on the same page here. So each of these dots here is one measurement of the brightness of a star. So you point a telescope at a star, it's kind of the most boring observing that you would ever do, is you point at the same place and you take images over and over and over and over and over again of the same thing. So for tests, that's an image every 2 minutes for a month of the same part of the sky. This is ground-based data over, you can see here, maybe about 12 hours. So it's still a long night of observing, so it's good to let your computer do that instead of having to click the button yourself. So each one of these is a brightness measurement, and this is when the planet is passing in front of the star. It's getting a little bit fainter, so this is time measured in hours. This is relative brightness here, and you can see in this case, it's getting brighter by about 0.5%, a little bit more than 0.5%. And that's about what you get for a Jupiter-sized planet in front of a sun-like star. So a good sort of benchmark number in your head is that the disk of Jupiter is about 1% of the area of the disk of the sun. So it blocks about 1% of the light. And here's just the super simple math down here. The area of a circle is pi r squared, as we all remember from our elementary school or high school. And so the fraction that the star gets dimmer is just pi r squared for the planet over pi r squared for the star. How big is the little circle compared to the big circle? And for most stars, we can get enough information about them from taking a spectrum that we've got a pretty good measurement of what the radius of the star is, just from what kind of light it's sending to us. And so by measuring how deep that dip is here, we can plug it in here and we can figure out what the radius of the planet is. So pretty cool for something that we can't even see. We can measure the radii of planets. So that's the basic technique. Okay, so here's an actual image of the test spacecraft in the clean room, and you can see it is much smaller than JWST here. It's more human sized. There are those 4 different cameras that I pointed out in the sketch before, and solar panels here, and an antenna for sending data back to Earth. If you're taking an image every 2 minutes, you can't store all that data on board forever, and you got to downlink it to Earth pretty frequently. Okay, so how do those 4 cameras work? It's kind of a cool arrangement in that it lets TESS look at a 90-degree field of view, at least 90 degrees in one dimension, at one time. So each camera has a field of view that's about 24 degrees on a side, and that pattern of 4 there kind of tiles them all together. So they're pointed in slightly different directions, and they can span all the way from the ecliptic, the plane of Earth's orbit, up to the ecliptic pole, exactly perpendicular to Earth's orbit. So that gives us a big chunk of the sky at one time. If you're going to survey the whole sky, you've got to think about how much you can do at one time and how long it's going to take. So this gives you maybe a different sense of that. Here are those 4 camera fields of view, and you can see them sort of tiled onto the whole sky here, 24 degrees wide, and then almost 100 degrees tall where it takes that chunk. So each of these, so TESS will point in one of these positions for about a month at a time. So it stares at that part of the sky for 27 days and takes images every 2 minutes and measures brightness of thousands of stars in each of those fields. I'll show you what one of those fields looks like in just a minute. And then to put it all together, this is how it kind of all builds up. So each of these chunks is a month. So all the way around half of the sky takes a year. So it started in the southern sky and surveyed the whole southern sky. Then the next year it moved up and did the northern sky. And so it has now finished one entire cycle of most of the sky, with the exception of a little bit of a chunk down around the plane of the ecliptic there to avoid the moon and the bright planets and of course the sun. But it has finished most of one cycle around the sky, and now it is gone back and starting to repeat some of those fields. So it launched in 2018, so in early 2020, kind of mid 2020, it finished its first map of the sky. And one of the things you can see here is that because each of these fields goes all the way up to the pole, there's an area, some parts of the sky only get observed for a month at a time, but there's an area up near the pole that gets observed in every successive field. So that's quantified here. Same kind of mapping here. Each of these slices is one sector or 1 month. And there's an area near the pole that gets observed continuously for almost a whole year. And by design, that's also an area of the sky that JWST, James Webb Space Telescope, will be able to point at anytime it wants to. It's so-called continuous viewing zone for JWST, because that's perpendicular to the plane that the sun is in. So when you're pointing up towards the pole, you're never pointing towards the sun. So that part of the field isn't blocked. So different parts of the sky get mapped for different amounts of time, basically. And so that helps us with being able to detect, in some cases, some longer period planets. Okay, maybe something a little bit more familiar, so I can say, 24 degrees on the sky, but how big is this? This gives you a sense of how big that is with our old friend Orion here. And so one of those 4 cameras, you can see sort of outlined here that each of the cameras has 4 CCDs in it. And so one of those 4 fields of view is big enough to take in all of Orion there in one view. And then there's 4 of those in each sector. So here's some actual data. So each of these sets of 4 here is one of those fields from those 4 cameras. So this was the very first part of the sky that TESS looked at. And because it was pointing towards the south, it got to see some things that we don't get to see from up here in the north, but which you may be familiar with, which are the two satellite galaxies of the Milky Way, the Large Magellanic Cloud and the Small Magellanic Cloud. So those are nice, nice views there. You can, and here's a zoom in to one of those individual CCDs, and you can see there part of the LMC, or the Large Magellanic Cloud. Those of you who do CCD observing and have sharp eyes here may have noticed that each of these CCDs has a little bit of a brighter spot there in the corner. That part of each chip is a little bit warmer because that's where the electronics are that read out the chip. So you get just a little bit of a glow there in the corners, and you can calibrate that out, but it's a little bit different because these cameras don't have shutters, and so it's a little harder to take the kind of dark exposures that you would on the ground. Okay, so that's some of the first test data. Here's another view of it where we've zoomed out all the individual 4 different fields there. So you can see all 16 CCDs. And if we were to zoom in, you can see that there's just thousands and thousands of stars in each of those images. So pretty big chunk of the sky. But as you might imagine, since it is a big chunk of the sky, if you zoom way in, the pixels are actually pretty big on the sky as well. So each pixel is about 20 arc seconds, 21 arc seconds on the sky. And so it's not super high spatial resolution at the detailed level, but good enough to separate out the stars. You're sort of trading off field of view of the whole camera and size of each pixel. Okay, so let's talk about some actual discoveries from tests. So this is some data that came out of the first sector. So this was middle of 2018. And here's a few objects labeled Large Magellanic Cloud. I mentioned before, since this is the southern sky, these aren't super familiar constellations to many of us, I'm sure. Doradus, Reticuli. I want to focus over here on a constellation that honestly I don't know a whole lot about, which is Mensa. Mensa is the table, named after Table Mountain in South Africa. So Alpha is the brightest in that constellation, but we're going to zoom up here in the corner and look at a different star, which is Pi Mensae. So you probably know the stars in each, bright stars in each constellation have Greek letters, alpha, beta, gamma, delta. So down to Pi here, still a relatively bright star, about 5th magnitude, 5.5 magnitude. And this star actually, before TESS was launched, was already known to have an object orbiting around it. I say object rather than planet because it's a big to be a planet. It's kind of right on the edge between being what we would call an exoplanet and what you might call a brown dwarf. And that was first discovered in 2002. But when the test data came in and people looked at it more closely, they discovered that it is not alone as a companion to this star, Pi Mensae. So this is work led by Chelsea Wang at MIT in analyzing some of these TESS observations. And so here's what the data looks like. And so there's a lot going on this slide. So I want to take a few minutes to kind of talk through it. So each dot here is a single brightness measurement of that star. And let's ignore the bottom one for a minute and just talk about the two on top here. The timeline here is given in days here. And so you can see if we're going from 8325 to 8350. So there's our 27 days looking at one part of the sky, and then its brightness on the y-axis. And so one of the things you can see is that the data coming straight off the satellite is not perfect. It's got some definite patterns in it. One of the things is that there's a missing chunk right here, and that there's another missing chunk right there. All test light curves have this because those are times when the spacecraft had to stop taking data and then downlink all that data back to Earth. So there's always gaps during that 27-day period. So these are data downlink times. The other thing you can see here is that there's some discontinuities in the light curve that come about every 3 days or so, 2 to 3 days, where the light curve kind of jumps. And those are what are called momentum dumps. So basically, the spacecraft is staying pointing at the particular part of the sky because of some spinning gyroscopes, what are called reaction wheels on the spacecraft. And those are able to offset some of the drift of the spacecraft for a certain amount of time, but after a while, then they have to reset. And so the spacecraft reorients a little bit, and it gives you a little bit of a jump in the data. It's well known where those are, so they can be taken out. And so here is the test data with some of these known artifacts taken out, and you can see very clearly this regular pattern of dips there in the data, spaced about every, in this case, maybe about every 6 days apart or so. And if you add all this up, if you sort of fold it on that period, then you can see very clearly the signature of a planet around that star. And so in this case, these numbers here, this ppm here stands for parts per million. So the depth of this is about 300 parts per million. And so that is less than a part per thousand. So it's like 0.03%. So it's a tiny, tiny variation in the brightness of the star, but you can see that it's no problem for tests to detect it. And when you take the radius of the star into account, this adds up to the signature of a planet that's about twice the radius of the Earth. And so one of Tess's first discoveries here is about a 2 radius Earth planet, so-called super Earth, something we don't have in our own solar system, but planets that are kind of 1.5 to 2 times the size of the Earth. Okay, so that's one discovery. Let's take a look at another one. So this is, again, first sector data. Here's the small Magellanic Cloud. So we're one field over from the one that we just looked at. And now we're going to zoom in on a much fainter star with a slightly more prosaic name here, LHS 3844. We've all run into these things in various catalogs, maybe. In this case, LHS stands for Luyten half second. And so Luyten did what's called a proper motion survey of the sky. And the half second there refers to the stars in his catalog that had proper motion across the sky of more than a half arc second per year. And that's a good way to find nearby stars that seem to be moving as they move across as you sort of compare them to the background stars. So this is a pretty nearby star, only 15 parsecs from the Earth, or about 45 light years. So this discovery was led by Roland van der Spek, who's one of the sort of hardware wizards of the TESS mission. And I say led by, so I'm trying to highlight some of the real people involved in these discoveries, but there's hundreds and hundreds of people behind every discovery. And these discovery papers typically might have 75 to 100 authors on them, but people sort of take turns being the lead for different discoveries. So this is a different kind of star than the sun. It's definitely at the very cool end. So just to give you a sense of scale, here's an image of the sun. Here is what I've labeled as LHS 3844. It's actually a scaled down image of the sun. But this star is actually much closer in size to Jupiter than it is in size to the sun. So the coolest stars and the smallest stars are only about Jupiter sized. So it's sort of interesting that stars can be not much different in size than planets. So this is a real small star, relatively cool star. But actually for the transit work, one disadvantage of these stars is that they're faint, but one advantage of them is that they're small. So remember, we said that the dip you get in the transit light curve depends on how big the planet is compared to how big the star is. And so I tend to usually think of that as like, well, to get a deep dip, you need a big planet, but you just need a big planet relative to the star. So the star being smaller means the same size planet is going to block more of the light than it would for a bigger star. So if we just think about Jupiter passing in front of this versus Jupiter passing in front of the sun, you're going to block much more of this star's light than you would block of the sun. So transits around these small cool stars, in some cases, if you get enough photons, are actually easier to detect. So here's the data. And on the, so before we saw, kind of some jiggles in the upper light curve, and then it cleaned up nicely in the detrended light curve, and you could clearly see the transits. This case, not so much. It's a much fainter star, so there's more scatter in the data. But the magic of averaging helps us get over some of that. As long as it's random noise, then it'll average out when we bin together more points. And so here is what we get if we take the test data and we add together a bunch of consecutive points to reduce the scatter. And you can see a very clear signal there. And in this case, I'm also showing what we do from the ground. So it's great to have tests make these discoveries, but we want to be sure we can reproduce them on the ground. So these are 3 different, or actually several different ones here. These are taken with ground-based telescopes, a little more scatter than the test data, but again, very clearly seeing the same event, the same transit event. So if you put all the ground-based data together, this is what you get, reproduces what we see in the test data very well. And this planet's even smaller, only about 30% larger in radius than the Earth. So 15 years ago or so, I used to tell my students when I was teaching, I said, people are doing cool things and discovering Jupiters, but I don't think we're ever going to discover an Earth-sized planet in my lifetime. So shows what I know. I did say when I would say that to them that, that I hated debate against how smart people could be and how much ingenuity people could have, but we're, not that long after I said that in the era where we can discover Earth-sized planets around other stars. One of the kind of interesting things about this star, you can see, or the system, you can see that transit's pretty short. So this is 1 hour here. So the whole width of that transit is only maybe 20 minutes or something. And that's because the planet is really whipping around the star. So this is obviously an artist's conception of this very red star and this planet in very close to it. But the planet completes 1 orbit around the star in only 11 hours. So a year on this planet is 11 hours long. Brian Jackson, who's an astronomer who studies some of these very close-in planets, likes to say about ones like this that you could watch the whole Lord of the Rings movie trilogy, and it would take you more time than it takes this planet to go all the way around the star once. So if you wanted to do it once a year, you'd have a hard time doing it because it takes more than a year in this planet's time to do it. So it's pretty amazing. We think of Mercury, at least I think of Mercury in our solar system as being very close in and having a very short year, only 88 days. So, but 88 days starts to seem huge compared to, less than half a day. So this is pretty cool. One of these super short period planets. So definitely we're seeing things that are nothing like what we see in our own solar system. Okay, give you one more in my kind of rogues gallery of planet discoveries here. This one was led by Andrew Vanderberg, who's now assistant professor at my PhD alma mater in Wisconsin, University of Wisconsin-Madison. And the WD in this name stands for white dwarf. And so this is a very different kind of object. So here's the test data. So each dot is a brightness measurement, and you can see the clear dip down there. These data, faint objects, so there's a fair amount of scatter there. If you take the ground-based follow-up data, super nice light curve here of this object. And I want to point out 2 things about this light curve that are pretty different from some of those light curves that we were looking at before. So you might say, well, all these graphs with dots on them look the same, but there's 2 super interesting things here. Number one, I pointed out, oh, this dip is, 1%, or it's 0.1%, or that one was like 0.03%. This dip is almost 60% deep. So here's one, and and 0 would be right here. So when this thing passes in front of the star, more than half of the light is getting blocked. The other thing to note here is that the time scale, these numbers are similar to what you've seen, but before I was showing you hours, now I'm showing you minutes. So this whole transit is about 7 minutes long. So it's tough observing to do because you can't expose for very long if you want to get this observation. So this is because this is a very different kind of object. So to give you a sense more to scale, here's an illustration where here's the planet. We think this is about a Jupiter-sized planet, and here's the star. So a white dwarf, I'll show you more about this in just a second, but a white dwarf is the leftover remnant core of a star like the sun. It's what the sun will end up as about 5 billion years from now, but it is super tiny. So the reason the dip is so big is that the star is really small. If this orbit was perfectly edge on, that dip would go all the way down to 0. It's tilted maybe just a little bit, and so the planet doesn't quite pass across the full face of the star. So we lose only 60% of the light rather than 100% of the light. And it's very close in, so the orbit is very short. So it doesn't take long to go across an object that's only the size of the Earth. So to give you a little bit of a refresher on stellar evolution here, I said the sun is going to end up as a white dwarf at the end of its life, but it's got to go through a different phase first. So when the sun starts to run out of hydrogen in its core to fuse, it goes through a phase called the red giant phase. So the sun will eventually swell up until it is, you see different things from different calculations, somewhere between 1 AU and a little bit more than 1 AU. Here it says diameter is 2 AU. So the radius is about 1 AU. So just to remind you, an AU is the distance of the Earth from the sun. So when the sun gets to the end of its life, it will swell up to encompass Mercury, encompass Venus, and at least get close to encompassing Earth. We'll be long gone from Earth because it's going to be way too hot by then, but the sun will get big enough to swallow all those inner planets as it goes into this red giant phase. And then eventually those outer layers will drift away, and you'll be left with this very hot core that's the white dwarf that's left over. So that kind of raises the question about this system is, how's that planet still there? How did that happen? Because the planet is actually really close to the star, much closer than what we think the radius of the white dwarf would have been. So here's just a little timeline cartoon in billions of years. We're at about 4.5 billion years. At about 10 billion years, the sun will become a red giant, much bigger relative to the current sun than is shown here. The outer parts will get sloughed off in this brief phase called the planetary nebula phase. Very beautiful nebulae, I'm sure you've probably seen. And then what's left behind is a white dwarf. So something about the size of the Earth. So to give you two different senses of scale for this system, let's look at the bottom first. So here is the relative size of the sun and of the Earth. Yeah. This white dwarf is much closer to Earth-sized than it is to Jupiter-sized. And then to give you a sense of distance scale, so here's our own solar system, Mercury, Venus, Earth, Mars, to scale. Mars is about 1.5 times as far as the Earth is. And so this is 1 AU, and this is about how big we think the red giant phase would be for this star. And yet that planet is currently sitting in right next to the star. And so this is a real puzzle, and it's a real weird kind of interesting system. Is we have a planet that is sitting in a region that would have been engulfed by the star at some time in the past. So one of the things about astronomy is we can't go back and look, or we can't wait and see, but we can build models and we can use the physics that we understand. And so So the idea here, here's a little animation that I'll kind of talk through as it's playing, but this is just to give you a sense of the scales here. So this is in where the planet is now, but this is just a little animation of the star becoming a red giant. You can see it would have totally engulfed where that star is now. The outer layers dissipate. And so, so this animation is going to show the planet moving out. So the timeline is really sort of reversed here, because what this is really illustrating is that we think the planet must have originally lived out here somewhere, maybe out where Jupiter is in our own solar system at 5 AU. And then later in its evolution, then it must have migrated inwards. One way that that can happen is that when the sun becomes a red giant and that material drifts away, as that material has drifted away, it no longer, the lost material no longer exerts a gravitational pull. So the pull from the central object is less, gravitational pull is less strong than it was before. And so some objects may migrate inwards, but we don't know exactly how the migration happened. But we know that planets that must migrate to get to where we see them today. So I think this is a super cool discovery that Tess has made, and a little bit of a puzzle. Okay, so those are some kind of a rogues gallery, some individual discoveries that Tess has made. What I want to do now is take just a few minutes before we open it up for questions to kind of try to put some things together and say, okay, we've discovered a bunch of planets. Some are weird, some are normal. But what do we have when we take all these things together? So let's kind of try to see some patterns. So here's a nice animation from Hugh Osborne. So what we're going to look at over time is a timeline of the discovery of planets. And so we're going to start in 1710, and we're going to run the clock forward, and you're going to see different points appear on this plot. What's shown on the x-axis is the period in years, how long it takes the planet to go around. So this green dot right here at 1 year, that's the Earth that goes around the sun in 1 year. And on this scale, this axis is the mass of the planet. So Earth, of course, is 1 when you express it in Earth masses. So these 6 dots here are Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Because in 1710, those were the only planets we knew about. So let me start the animation here, and we'll see this plot start to get more populated. So we'll run through the 1700s. Here, Uranus is discovered. Mid-1800s, Neptune is discovered. Early 1900s, we'll see Pluto pop up there. And then in the 1990s, we start to discover planets outside the solar system. We need to slow the clock down a little bit. First with the radial velocity method, then with the transit method. The Kepler mission gets launched in 2014, and things really start to take off. And we get up to the 4,300 planets that we know today. So there's a lot going on. I've said this a few times about plots. There's a lot going on in this plot, so it's worth talking it through. So I want to use this as a way to kind of illustrate some of the things we're starting to learn about planets, not as weird individuals, but as groups. You know, in our own solar system, we have the small rocky planets in the inner solar system. We have the more gaseous planets in the outer solar system. Other solar systems, we see some things that are a little bit different. The first thing that I'll point out, which maybe is obvious, but it's worth noting, is that dots are not randomly distributed in this plot, right? There are some clear patterns and areas with a lot of points and areas without very many points. The first thing I'll note is if we sort of draw a diagonal line from lower left to upper right here, obviously the upper left part is more populated than the lower right part, and that is largely a selection bias. It's easier to detect planets that are more massive, and it's easier to detect planets that go around their star more frequently. Those generally give you a bigger signal and you have more chances at them. So the fact that the lower part of the diagram is less populated is telling us more about our technology than it's telling us about the population of exoplanets. But even if we concentrate, even if we say, let's draw a line here and we concentrate on this upper part, there's some clear patterns here that now are not selection biases. So the first thing I'll point out is these yellow points is we've got a clear population of things with sort of 100 to 1,000 Earth masses. So just for reference, Jupiter, so there's Jupiter right there. So Jupiter is about 300 Earth masses. So these things are sort of a third of a Jupiter mass to 3 Jupiter masses. So these are the so-called hot Jupiters, things that are very close to their star and that are about a Jupiter mass. And then down here, kind of 1 to 10 Earth masses, these are what are referred to as either super Earths, or sometimes there's Neptune there, mini Neptunes. So there's a whole lot of these planets. These seem to be the most common planets. But one interesting thing is there's nobody home right there. So why is that? That's kind of interesting. These planets would be easy to discover if they were there, and they seem not to be. So among the very close-in planets, there's this clear dichotomy between things that are pretty big and things that are pretty small, and not a lot of planets in between. And so people sometimes call this the Neptune desert. There seems to be not very many kind of Neptune-sized planets that have migrated in close to their stars. So that's one pattern that has emerged. Also, you can see a cluster of purple points here and a cluster of yellow points here, and not a whole lot in between. So these are planets more or less like Jupiter. So again, that's Jupiter there. So masses are Jupiter-like, distances from the sun. So this is given in years, but you could also think of this as distance from the star. Those two things go together. The farther out planets take longer to go around. So these are kind of the Jupiter-like Jupiters, and these are the hot Jupiters, and there's not much in between. So whatever process moves things from one to the other apparently makes them keep going and not kind of get stranded in around, Mercury or Venus's orbit in here. So that's a distinct population. So kind of almost 3 clusters of planets here in ways that aren't explained by what we can detect or can't detect. It would be pretty easy to fill this in. It would be pretty easy to fill that in. And it just seems like those planets aren't there. Technology-wise, I'll point out these guys out here. So these are different techniques here. And this is labeled as imaging. So we're just starting to be able to actually take pictures of planets around other stars. It's easiest when they're far from the star because it's the brightness of the star that makes it hard to see the planet close to it. You tend to think it's because the planet's faint. It's not so much that the planet's faint, it's just that the star is too bright and the contrast is too high. But this technology is really starting to improve. And so we'll be able soon to take pictures of planets that are fainter, but also that are more closer to the star. So I want to relabel all the planets in our own solar system and use them to kind of point out a couple more things about this before we wrap up. Number one is, here's Mercury. It takes 88 days to go around the sun. And, I mentioned when we were talking about that 11-hour planet, it's like, I used to think of Mercury as a close-in planet. It is striking to me how far out in this diagram Mercury is. So in some ways, the picture that I've sort of come to is that we don't have to answer why is Mercury so close to the sun. What's puzzling about our own solar system is why don't we have planets closer than Mercury to the sun? Because everybody else seems to have them. Almost every planetary system we see has a planet closer than Mercury to its star. So what happened in our solar system that made us not have one that's in quite that close? Detection-wise, I'll say it's pretty tough. We're still not really quite able to get down to things with Mercury's size or Mercury's mass if we think vertically on this graph here. Okay, so here's Venus and Earth. So I mentioned this part of the diagram is a little lonely except for the solar system planets, but I'm sort of talking through, what what do we know now, or what's maybe coming in the future? We know of a lot of Earth, I was gonna say Earth-like planets. That's not quite the right thing to say. We know of a lot of Earth-sized planets now, hundreds of them. But what we don't yet have very good examples of, not zero examples, there's one right there. We don't have sort of Earth-sized planets at Earth distance from the stars. One thing that will help here is better technology, but another thing that will help is just time. As we go farther to the right on this diagram, it just takes more and more time to detect things that take this long to go around their stars. But we're starting to get the detected extrasolar planets close to this part of the diagram. There's some transiting planets that are just a few times bigger. There's some mass measurements that are just a few times larger here. The purple is the radial velocity method, which can measure the mass rather than the radius of a planet. And there are big advances coming in a new generation of telescopes and instruments that will start to push down into detecting Earth-like planets at Earth distance from a star. That's something that's coming. Mars is going to be tougher because you can see, I tend in my mind to group together Mercury, Venus, Earth, and Mars, and especially Earth and Mars, because we're such close neighbors, but Mars is really a lot smaller. It's only about 1/10 of the mass of Earth. So that's going to be a tough one. Jupiter and Saturn here already have a little bit of company. We're starting to see Jupiters at Jupiter-like distances. They seem not to be super common. Maybe 10% of systems with planets seem to have a Jupiter in them. The Earth-sized planets are much more common. And then we've got Uranus and Neptune out here. And we have a big population of sort of Neptune-sized objects that are close in. We're not yet quite able to get them out at that distance. And that's partly because if we look down here where we are on the x-axis, that's 100 years. Takes Uranus almost 100 years, takes Neptune more than 100 years to go around. And so about, I would say, you can sort of almost even see it on this diagram, about right here is about the amount of time that we have had the technology to detect extrasolar planets. About 20 years, 25 years right there. And so this will keep pushing out as we get more data, and we'll be able to discover more things in this part of the diagram. The imaging is going to get better. JWST is going to help push down, and we'll start to be able to, I think, in our lifetimes, in the next decade, we'll start to see more images of planets around other stars as well. So we've learned a lot already, but we definitely have a lot more to learn as well. So I'll stop there and just conclude a couple things. TESS is still flying. It's still working well. It's still making discoveries. About 100 planets have been published, but I can tell you from the work I'm doing right now, there's a lot more to come. There's papers in press. We've got about 1,000 candidates we're actively following up. Not all those will turn out to be real planets, but there's more coming. JWST is going to launch this fall, I hope, fingers crossed. And so we're really in an exciting time about learning more about the universe, and especially about planets around other stars. So I'll wrap it up there, and I'll just leave up here a couple web links. Bruce mentioned some software that I've written. If you want to make observations of transiting planets that are known, I've got a website that you can enter your location, and it'll tell you what's transiting tonight and give you coordinates and a finding chart. There's a nice visualization of a bunch of the test data there. And if you want finder charts or air mass plots, I'll leave all these up there. I'll also share them with Bruce. If any of those tools are useful to you, I'm happy to have you use them. And I would also be happy, thanks for your attention. I'd also be happy to answer any questions you have. Thanks a lot.
So Eric, this is Bruce. I have a question. Based on sort of collectively what we know to date, right, of various exoplanets, you made the comment about WD 1856b. Can it be said that in general, we think in a lot of exoplanetary systems, planets originated at one point and over time migrated inward toward their star, which may explain why they're so close? Or do we think that's not that common of a phenomenon if we look, across all the exoplanets that we've discovered?
Yeah, that's a great question. It's a little, so certainly we know that migration of planets seems to happen a lot.
We're sharing a screen, that's why.
We see all these close-in planets that probably didn't form there. We see things like that white dwarf planet. What makes it a little bit hard to answer is we're also a little bit biased towards those planets, right? So if planets have migrated in, they're easier for us to detect than if they have stayed out where they are. That said, even if we only take the planets that we already know about, the biased sample we already have, and say, what fraction of stars have planets, the fraction is pretty high. And so, if you take into account multiple planet systems, the average is about 1 planet per star in our part of the galaxy. Now, that doesn't mean, that means some stars we haven't detected planets and some stars we've detected 3 or 4. But still, it's not like it's only 1 star in 100 that has a planet. A lot of stars have planets, and a lot of those planetary systems show evidence for migration. And so I think it's pretty common for those to move around. There's also some pretty good evidence now that that Jupiter and Saturn and Uranus and Neptune are not now in the solar system exactly where they formed, that they've maybe moved around a little bit, that Uranus and Neptune in particular probably have moved out. So seeing the extrasolar planets has, along with new missions in our own solar system, has helped us kind of look at our solar system with fresh eyes too, and see some evidence of migration there. Now, one thing that also biases our sample is that if in our solar system, Jupiter had moved all the way in to inside Mercury's orbit, we wouldn't be having this conversation right now because Earth would have gotten taken along with it. So it may be the solar systems where the migration isn't quite as catastrophic that are the ones that are a little bit more hospitable to life, but we don't really know that for sure. But yeah, it's a great question. But yeah, migration is a big part of the story, it seems like, in understanding these systems.
Thanks.
I have a question. How do you determine whether a planet is like a gas planet versus a rocky planet? Can you tell that from your data?
Yeah, that's a great question. So what helps the most, so I'll step back, I guess, to here. What helps the most is the systems where we can get 2 different kinds of data. So this transit method that I mostly talked about gives you the radius of the planet, but it doesn't tell you whether it's gaseous or rocky. It doesn't tell you what the mass is. But for a lot of those planets, then we can also go back and use a different technique of measuring how much the star wobbles as the planet goes around it. And we can also get the mass. And so the systems we know the most about are where we've used both of those techniques to get if you get the radius and you get the mass, then you know how dense the planet is. You know if it's sort of a puffy gas giant or if it's a small rocky planet. So these systems kind of divide into different groups based on that. But for a lot of them, we can get both of those kinds of data.
Do you have a chart or anything that shows like which ones will be rocky and which ones will be gaseous planets?
Yeah, I don't have it right here, but typically what we find is that anything that's sort of Jupiter sized here also ends up being gaseous. So we haven't found anything that's like 300 times the mass of Earth, but has the density of Earth that is consistent with being all rock. So basically, all the big planets are gaseous. The smaller planets that have sizes more like Uranus and Neptune, we see a little bit of a split there. Actually, let me jump ahead. I gotta step through those. Let me jump ahead to an extra slide that I have here. And so this is the radius of the planet compared to the Earth. So Earth would have one Earth radius here, and then this is something 2.5 times there. And then this is how many planets that we see. And the interesting thing is there's a peak here of a population of planets that are about the size of the Earth, maybe a little bit bigger. And then there's a bunch of planets that are maybe 2.5 times that radius. But there's a gap in between. So it's these gaps in some ways that are interesting, because if we can detect these, we should be able to detect those. So what we think is going on here is that that these are rocky, and these have a rocky core, but also are sort of like Uranus or Neptune, that they have a gaseous atmosphere as well. And so that somehow these either never had an atmosphere or they lost it, and these have managed to hang on to a gaseous layer, and there's sort of two different populations here.
Okay, so then how would Venus fit into that chart, since it has a gaseous
Yeah,
atmosphere?
so Venus would be right. So atmosphere maybe wasn't quite the right term. So on Earth and Venus, there's an atmosphere, but it's super thin. It's like if you had an apple, it's thinner than the skin on the apple. Uranus and Neptune, it's more like a layer that's maybe 20% of the radius of the planet or something like that. You know, it's like wrapping your apple in a big bunch of cotton or something like that. So these have, yeah, not just an atmosphere, but a big gaseous layer that's sort of like what Jupiter and Saturn, or especially Uranus and Neptune, have.
Thanks.
Yeah.
Eric, is there any way to tell the age of an exoplanet?
That is a great question and a vexed question, because people would sure like to know, right? Are we looking at young systems? Are we looking at old systems? How much time have they had to evolve? So basically you tell the age of a planet from the age of the star. And so the working model is that, and with lots of evidence for it, is that stars and planets form at the same time. We see very young stars surrounded by gas and dust. That's the raw material for planet formation. And so different kinds of stars are easier or harder to get good ages for. But it's age dating the stars is what we use to age date the planets. And that's one of the sort of frontiers, maybe is a little too strong a word, but active areas of research right now is trying to find younger and younger stars and see if they have planets around them, and also trying to look at very old populations of stars and seeing if their planetary systems look different.
Okay, yeah, because I was wondering if maybe the Jupiter planet formed after the white dwarf star became a white dwarf.
Yeah, that's a good question. I mean, so we see, for example, a couple of pulsars that have bodies that we think formed afterwards. I think the working model is that you might be able to form very small things, but it's probably tough to form something as big as Jupiter afterwards. With the white dwarf, there's just not enough. There's not enough mass. There's not dense enough mass around for that to coagulate and form. So the working model is that maybe if you saw a small chunk of debris like the size of Mercury or something, maybe that could be leftovers. But something the size of Jupiter is probably hard to form later, and so probably had to come from before.
Eric?
Yeah.
I have two questions. One is,
okay.
How many planets do we have, exoplanets that we found that actually are in the Goldilocks zone? And secondly, what is our technology change for the future to try to find more Earth-sized planets?
Right. So to answer the first question, the so-called Goldilocks zone or habitable zone is the distance from the star where there could be liquid water on the surface of a planet. So in our solar system, that's sort of between the orbit of Venus and the orbit of Mars, roughly. For cooler stars, it's closer in. And in terms of number of planets that we've found there, let me jump back here. So if you look at kind of 1AU, so these are not all sun-like stars, but a lot of them are not too different from the sun. We found a decent number of Jupiter-like planets there. But in some ways that's less interesting, or at least in terms of a very Earth-like solar system, because there's no solid surface of these planets. Now you could have a moon around one of those that could be, could have liquid water. But down here is about where that would be. I don't have that's a good question. I don't have an exact number for you. I would say maybe dozens, you know, I don't know, 30, 40, something like that, if I had to make a guess. But that number is continuing to go up, and it's partly populating more planets here. It's partly looking at cooler stars where that zone is closer in as well. To answer your second question about what's the technology that's going to help us detect Earth-like planets, all these purple points that are labeled RVs is the so-called radial velocity or wobble method that measures the motion of the star, the wobble of the star as the planet goes around it. The smaller the planet is, the less the star moves in response to it. And the big advance is in new instruments that can measure smaller and smaller and smaller velocity shifts in the star. So measuring a smaller velocity shift gives you sensitivity to smaller planets. And so there's a new generation of instruments coming along that is just starting to take data that's going to start to fill this in more, because they can measure smaller wobbles, basically, can measure more precise velocities.
Okay, thank you.
Yep.
My name's Athena. I have a question.
Yeah.
Is there anything, I don't know a whole lot about this, so I'm not sure how good this question is. But is there anything we've learned from TESS about improving the technology that we're currently working with for satellites and other spacecraft?
Good question. So what, anything about the mission, like what lessons have we learned from the mission to help with things? I'm not quite as involved on the hardware side of things, and so I'm not sure of the answer to your question. I think partly what's helping there is just getting a better sense of what, this is a little bit in a different direction than your question, but getting a better sense of what kinds of planetary systems are out there, and therefore what the next generation of instruments would have to be able to do to be able to detect them. So it's not so much that we've learned, this hardware doesn't work very well, but it's more like we've learned, oh, there's a lot of these things there, and so the next telescope we build had better be good at looking for those things to do it. Yeah, good question.
Thank you.
Got a question that has two parts to it.
Okay.
First of all, we've talked a lot about the space telescopes and the improving technology there. Would you perhaps comment on whether or not some of the ground-based super telescopes that are coming online now and in the very near future are going to be either impacting this data either to confirm or extend some of the observations that we've gotten from the space telescopes? And the second part of the question is just how weird is the Sun-Earth system? I grew up thinking that our sun was, way back in the dinosaur ages, that our sun was just a typical star among maybe a couple million stars in a rather average galaxy and the vast emptiness of space. And almost every time I turn around, we turn out to be weirder and weirder and weirder. How far off the bell curve are we?
Yeah, okay, so good question. So there's two different questions. So I'll take the first one, and I've kind of already answered it, though I didn't say so very explicitly. So I mentioned this when I had the previous question about what's going to let us detect more Earth-like planets. And I mentioned there's this new generation of spectrographs that can measure very small wobbles or very small velocities. Those are all on the ground. Those are not space-based telescopes. So those are on ground-based telescopes. So almost all these purple points here are measured from ground-based telescopes. So it's the ground that lets you have the stability of being able to measure those very small wobbles. And so part of that is ground-based telescopes that have more precise spectrographs. Part of it over in the upper right of the diagram here is also ground-based telescopes that have better and better what's called adaptive optics systems. So that lets you push the resolution limit. So it's a combination of adaptive optics to get very good spatial resolution and active techniques to suppress the starlight. This is one of the weird parts of astronomy where to try to image planets, you're trying to get rid of as much of the light from the star as you can because you want to see this faint thing that's next to it. And so that technology is improving as well. And that's mostly ground-based. JWST though will help with that imaging there. As far as how weird or how normal our solar system is, you can partly, so we're starting to get a sense. So I talked about that or alluded to that a little bit when I was talking through this diagram, but partly the fact that this lower part of the lower right part of the diagram is pretty empty, I think is still mostly because, so it could be empty because there's no other solar systems like ours, right? But I think it's still mostly because of limitations of our technology for being able to detect the planets like the ones in our own solar system. We've got more of a sense now that that Jupiters are not super common. I mean, I say words like super common. What does that mean? Occurrence rate of Jupiters is maybe 10% or so of stars. Is that a big number or a small number? I don't know. You decide. 1 in 10 is a lot more than 0 in 10, but it's a lot less than 100%. Multi-planet systems certainly are common around stars. Planets in general are common around stars. So we have that in common with the rest of the universe. But how common are Earth-like planets at Earth-like distances? That's going to take us maybe another few decades to start to answer. We're not total oddballs, but there's some nice variety out there. Let's say that.
Thank you.
I have a question, and that question is from the distance, from a very specific distance, how detectable would the planet Earth be out in space, considering that the only time that it would occlude the light from the sun would be a very, very short period of time, and we would have to catch it.
Yeah, that's right. I mean, so it's tough. Right. And so if you wanted to detect it from the transit method, you can draw a line along the sky, along the plane of the Earth's orbit. So only stars that are lying right along that line and looking back towards Earth are going to see any of our solar system planets pass in front of the sun. That's a reason sometimes, this is a little bit off topic, but people who do SETI sometimes look more in the plane of the solar system because maybe those other civilizations detected our Earth and maybe they'd be listening or something like that. So there's a limited number there. The wobble signal measuring the radial velocity is small. We're starting to be able to do it so basically if we could do it to them, then if they have the same technology, they could do it for us. So it would have to be an advanced technological civilization to detect it. But we're proving on Earth, I guess, that's possible. So the real answer to your question is, you tell me how common technological civilizations are, and I'll tell you how many people can detect Earth. I don't know. I don't think we have any idea what the answer to that question is.
Well, I was thinking that, in particular in our solar system, a much greater wobble would be accounted for by Jupiter's and Saturn's rather than Earth's or Mercury's.
Yep.
And the Earth could very easily be lost in the data points.
Yes and no. The thing that saves you with that is that they're on very different time scales. So you're right that the big planets give you more of a wobble, but it changes at a different rate. So that's how we've been able to do this with other systems. You know, some of these dots up here, we know of multiple planets in the system because we see wobbles in the data that are sometimes a combination of long and slow ones and shorter period ones. And so if you get enough data, then you can sort those things out from each other. But for sure, initially the data looks like a mess because things are going all over the place and you got to try to get enough data to sort it out.
Eric?
Yeah.
Assuming that we can develop the technology, might it be possible at some point by doing an analysis of a planetary atmosphere to determine whether there is life on that world?
Maybe. We can, so people think about this a lot and they think about what are called biosignatures. So could you know, so one way to detect life is for little green men to arrive at Earth or to send us a technological signal. But another way is to see something in the atmosphere that should only be there if life is there. Some kind of non-equilibrium chemistry people talk about, you know, so something that, you know, if it wasn't constantly being replenished in the atmosphere, would naturally come back out through natural processes and so shouldn't still be in the atmosphere. The methane in Earth's atmosphere, for example, is related to that. A lot of that comes from living things on the Earth and it would cycle back out pretty quickly. One of the things that James Webb Space Telescope is going to be good at is actually starting to detect atmospheres of other planets. I didn't really talk about this in detail or really at all, but let me try to give, I don't have a slide for it, but I'll try to give you a rough idea of how it would work. So if we go back to this image of Venus here, and if you think about a planet, that had a big atmosphere around it, when the planet is transiting in front of the star, some of the star's light is shining through that planet's atmosphere and reaching the Earth. And so people have done this for a handful of the known extrasolar planets, which is to observe them in transit and very carefully examine that light that you get while the planet is transiting and compare it to light when the planet's not transiting and look for signatures of the light going through the planet's atmosphere. And so JWST will be able to do some of that. Will it be quite good enough to get, you know, solid evidence that there has to be life on that planet? Probably not. But we'll start to get some indications of, is there water in the atmosphere? Are there some other compounds in the atmospheres that are interesting? The data that we have so far has indicated a lot of planets have pretty cloudy atmospheres where it's hard to get much information about their composition. And so that's a little bit of a challenge there. But that's something that's coming as well, is measurements, not just of planets' masses and radii, but some information about their atmospheres.
Thank you.
Well, if there are no other questions, Eric, thank you so much. Your talk was great, and thank you for taking so many questions from the group. We really appreciate it. Thank you.
You are very welcome. It was my pleasure to get to talk to everybody here, and I look forward to the time when we all get back together in person.
We look forward to that too. Thank you very much.
Thank you so much.
Thank you.
Thanks very much.
Thanks very much.
Bye.
Don?
Yeah.
I'd like to point out, although we didn't have John report and so on, I would like to point out that there is going to be a rocket launch down at Wallops Island on February 20th at 11:36 a.m. It will be the Antares rocket with the Cygnus capsule on it, and it'll be headed to the International Space Station.
Wow.
So that's something to keep in mind.
Road trip.
Yeah, road trip. Yeah.
Thank
Pete,
you.
Pete, what's
Sure.
the date again?
It's February 20th.
20th. you said.
Saturday. That's a Saturday.
Yeah, yeah.
At what
on a
time, I'm
Saturday.
sorry?
It's 11:36 a.m.
Okay.
Hey, Pete, how far is that from here?
From us? Oh,
How
you can
far?
see. Huh?
Drive?
It's far.
I
It's
just
far.
went down there for the rocket launch, but it's down there. It's down there by Chincoteague.
Like Chincoteague.
Yeah.
4 hours
Takes-
probably.
It's a long.
It takes me 4 hours from here.
Yeah, so maybe 5.
Yeah, it's a little bit of a drive.
It's
But
a nice drive.
It's well worth it to get down there and see that rocket launch. I'll tell you, I've been down there.
If it goes off.
Right.
Well, when I go down, I always plan on staying there for a couple days. Because I've been down there for many of the launches that didn't go off on the time and so on, including that one that blew up.
Oh, that's right. You were there, weren't you?
Yes, I was.
I do. Yeah.
That's why it blew up.
I was less than a mile away from that rocket when it blew up. They don't allow you to watch. They don't allow you to watch the rocket launch from the spot I was at. But I did find another good spot.
Is there a good B&B down there, or places to stay?
Well, we usually stay at a motel down there.
That's what I did.
In Chincoteague.
Yeah, there's a lot. I mean, and at this time of year, there's, outside of COVID, this time,
I don't know how
this
they
time of
open
year
right
would be very reasonable prices too.
Yeah.
I would tend to say so.
There's a KOA campground that has little tiny cottages you can rent also.
Yeah.
With heat?
Stay away there.
I think there's a motel called the Rosebud Motel.
Yeah.
There
Oh, you Schitt's Creek fans?
There's a lot of motels down there, believe me.
There's a lot, yeah. And and right, the last time I checked, I think it's still probably closed, but the NASA Visitor Center there had been closed because of COVID too. So
yeah,
well,
disappointing.
Like you don't want to really observe from the visitor center.
No,
That's
but you want to
5
buy
miles away.
souvenirs. You want to buy souvenirs.
Yeah.
But if you're going down to observe, you want to go to a place called Pettit Point.
Pettit Point.
Pete, I couldn't tell you how long it took me to find that doggone place. I mean, it's not
Pettit
easy
Point.
to find.
But
I ended up watching it from the visitor center because it was like the middle of the night, and I felt more safe there, I guess. But
First time I was down there for a rocket launch, I was there at the visitor center, and when I'm sitting there in their stands and so on, all you see is this little tiny white needle off in the distance alongside of a tower. and at that time, the launch got canceled. So the next day, I went out searching for a spot, and I found some other spots. And like I say, Pettit Point's one of them. Now, at Pettit Point, you're sitting there, you're looking out across the water, and without a pair of binoculars, a naked eye, you can see the American flag on the side of the rocket.
That's pretty cool. So let me ask you, I've tried to see it launch from here, right? And I know there's a delay generally, right? But I've never really found a good spot to actually observe because
Yeah, well, yeah, you'd have to have a good southern
horizon
sky and so on. Yeah, down to the horizon and so on.
I just don't know where to go. I seem, this whole area, unless you're down at the Chesapeake.
Well, I've known people have seen a rocket go up from down there, from all the way up at Cherry Springs.
That's impressive.
But this is going to be a daytime launch.
Yeah.
So it may not be. It's not going to be quite as evident as a nighttime launch.
Yeah.
I've seen it at night from my roof, actually.
Oh yeah. I've been down there for nighttime launches, and that's pretty spectacular.
Yeah.
But even from Pettit Point, if you're observing from Pettit Point, you are just a little over a mile away from the rocket. And it's just, it's water between you and the rocket. And when that thing starts launching, you can feel the vibrations in the ground.
That's cool.
And you get the full impact of that rocket launch. You feel the vibrations in the ground. As that thing starts lifting up, and it's kind of looks like over top of it, you can feel the heat on the engines.
Oh, very cool.
I don't know how much more of a experience you want to get than other than being on the rocket itself.
Yeah.
How early would you have to get to a place like Pettit Point to get a
Pardon?
spot?
Oh, I usually get there at least 2 hours before. Otherwise, you're going to be in for a long hike. It's only a little two-lane road leading to Pettit Point.
Okay.
And if you aren't there, there's a little park. It's a little park, and there's some parking area there. Now, you got to get there early because all the people from Northrop and all the contractors for that rocket usually have a party and everything else going on there because that's where they come to observe. And there'll also be a NASA camera set up there and everything else. So you want to get there early. That road will get cars lined for, I don't know how long. I wait till them all clear out, but when you look down that road, you just see cars parked on either side for as far as you can see. Put it that way.
Thanks.
So what it amounts to, if you get there late, you got a long walk to where the good site is, and you got a long walk back.
Gotcha.
So you were just there trying to get in on the party with the launch crew.
Oh, that's part of the festivities. They'll have speakers set up. You can hear them in the the countdown and everything else going on.
It wasn't the keg of beer.
That helps.
A lot of potty stops on the way, I'm sure, right?
You also get a chance to talk with those people and hear their little stories about what they're doing with the rocket, what their part was with it and everything else.
Where in relation to the flight facility is Pettit Point? I'm trying to find it on the map right now.
Yeah,
All
that's
right.
a good question.
It's south.
That's what I thought.
It's on the south side.
Is it near Wishart?
Because you go right by the gate for Wallops Island flight facility. In other words, if you were to go from the visitor center, you turn around and you go back from the visitor center, and you'll come to I think it's the first traffic light there.
The Royal Farm.
There'll be a
Royal Farms.
Huh?
The Royal Farms is right there. Yeah.
The Royal Farms right there.
Yeah. Mm-hmm.
Turn onto that road. Turn left onto that road where the Royal Farms is, and just keep on going on that road. You'll come to the intersection of where you drive out to the well, you can't get out there, but how you get out to the island, Wallops Island. You continue on that road straight on past that. And you just keep on going on that thing till I think you get to Pettit Road. It'll be on the left-hand side. And then you turn left on that road. And then there'll be another left. I don't know what the name of that road is. All you have to do is just follow all the traffic. Because everybody will be headed to the same spot, believe me.
Guys, I got to go. Let me tell you how much I enjoyed being with you this evening. It's been a pleasure. Take care.
Thanks for joining, Jack. Thank you.
Good to see you, Jack.
If you go past where the launch facility is, and you come to a little farmer's lane with MPs guarded, that's where I used to watch it from. They don't allow you down it anymore.
Because of you.
Yeah, well, they actually, when the rocket blew up, they evacuated us out there really quickly